This lecture is on the orbital notation, the boxes with the arrows that we've talked about, and it's on excited state configuration, ground state configurations, a little bit of valence electrons, and electron dot diagrams to close out the unit. Okay, so bless my cat. Any case, we should be very well versed in how to do electron configurations. We read the periodic table today, bless my cat again, and we notice it sequentially fills in order. So if this is the electron configuration of nitrogen, of course this would be 1s2, 2s2, 2p4 for oxygen, and this would be 1s2, 2s2, 2p5 for fluorine. And neon, of course, 1s2, 2s2, 2p6, that magical filled energy levels we talked about. Neon having not one, but two filled energy levels, okay? And that's what makes it stable. The driving force in the reactivity of metals is their ability to achieve the same stable electron configurations as their counterparts. Okay, notice that these chemicals all have to do is gain, this case, this one gains 2 to have 6. This will gain 1 electron to become 6, and this guy doesn't gain any. Okay, and we talked about the electrons that are available for bonding to be valence electrons. So if you look at everything before neon, we notice that this energy level is filled, not available for bonding. Therefore, carbon will have 4 valence electrons. Okay, that's not what I wanted. And of course, is my 4 valence electrons. Nitrogen would have 3 plus 2, 5. I'm just counting the electrons here. 4 plus 2 is 6, and 5 plus 2 is 7. And this coordinates, like I showed you in class, the column number. All elements in the same column have the same valence electrons, but gives them the similar properties. Fluorine loves to become F negative because when it gains 1, it becomes the same configuration. Oxygen loves to become O negative 2 to gain 2, and so forth and so on. Any case, my cat's still sneezing. Now, neon doesn't have any charge associated with it because it's stable. It has 2 stable configurations. All right. Bless you. Wow. Okay, so sodium, of course, has 1, and it has 2 filled principal energy levels, so it has these 1 valence electron. That's why it becomes Na plus 1. So the driving force and why things become ions, and essentially why they bond, is because of their electrons that are available and their ability to become stable. So it's easy for this guy to lose 1. All right, in any case, that's a little bit of review. Now, how these electrons exist in the sublevels, we deal with something called orbital notation. For instance, we know nitrogen is 1s2, 2s2, okay, 2p3. Now we know that these boxes represent orbitals. And an orbital is a place where 2 electrons can exist. Now we draw a box. These things actually have 3-dimensional shapes that we're going to get into. But right now, all we need to know is that 2 fills electrons. We know that the S holds 2 electrons. The S block holds 2 electrons. So therefore, this only has 1 orbital. Okay. This S block, like all S blocks, also only has 1 orbital per sublevel. Remember, it goes principal energy levels, sublevels, and now orbitals. That's the organizational pattern of electron. Now, the p orbital, remember, the p block has 6 electrons, so it has 3 orbitals, 3 places where they pair up together. Now, how they fill is very important. It's based on Hud's rule. And very simply, electrons fill empty orbitals first before pairing off. And the reason behind that is due to electron-electron repulsions. Why would an electron, okay, want to pair up in the same orbital and repel itself and have a high energy when it can be by itself? So electrons will choose, if they have the ability to, empty orbitals of the same sublevel before they're forced to be paired up. So this is why we would never draw the orbital diagram for nitrogen this way. Okay, now we don't have that scenario for S or 1s or 2s because they only have 1 sublevel. So let's look at oxygen. Okay, we know that oxygen, and I'm assuming we can draw these configurations, is 1s2, 2s2, 2p4. Okay, so I have one electron going one way, another electron going the other way. These double arrows are showing how electrons are repelling themselves. They have something called opposite spins. Okay, and electrons, and people don't quite get what that means, but they have opposite spins. A guy named Pauli found that electrons in a magnetic field will bend one way or the other based on their spin, and about 50% of each will go one way or the other. But all we can think about now is these arrows mean electrons are repelling themselves into opposite directions. But there's something more to that. In any case, 2s2, we have the same scenario. We have no other choice for electrons but this one orbital or box, so therefore there's no problems. 2p4, well, one would go here, another would choose an empty orbital, another one would choose, and now we're forced to pair up. And that's the proper orbital notation. Of course, this is 1s2. And by the way, for those that don't know, I'm using the notes that I printed out for you. Okay. All right, moving on. Beryllium. Okay. Now, beryllium, okay, is, I believe, 1s2, 2s2. Okay. And so, therefore, we would have this scenario. And again, because we're dealing with S's, there's only one box for S. Don't think that this one electron will come out to the P. It's a 2s electron, and only does so when it gets excited. We'll talk about that. So we're moving on. Now we have phosphorus. Okay, the configuration of phosphorus. Okay, and again, we can look at the periodic table, and we can see that phosphorus. Now let's zoom out here. We can see that phosphorus is, one more time, is 1s2, 2s2, 2p6, 3s2, 3p3. All right, 1s2, 2s2, 2p6, 3s2, 3p1, 2, 3. So let's put that in to what we were doing. So 1s2, 2s2, 2p6, 3s2, 3p3. So 1s2, 2s2, 2p6, 3s2, 3p3. Okay, let's put in the electrons. Okay, 1s2, 2s2, 2p6. So this is going to be entirely filled. 3s2, 3p3, 1, 2, 3. So what we're going to have here in this scenario is 3 orbitals with single paired electrons or unpaired electrons. Now, it's important that you be able to do this based on Hud's rule where electrons will go to empty orbitals because there are some questions that can result from this. For instance, from this configuration, I can ask a couple different questions. I could say to you, how many filled principal energy levels do you have? And you would say, okay, 1, 2, that's it, 2. How many partially filled principal energy levels? And you would say, well, this fills 1, this fills 2, so there's 1 partially filled. Then I could say, how many completely filled sublevels do you have? And you would say, okay, I have 1 S that's filled, this S is filled, this S is filled, this P is filled, ooh, this S is filled, so 1, 2, 3, 4. How many partially filled sublevels? And you would say, oh, this P is partially filled, so 1. Then, and here's the kicker, I could say, how many partially filled orbitals? Okay. Now, if you were to not consider Hud's rule and pair these up singly like I did, you may think, well, this is definitely filled. That's 1, 2, 3, 4, 5. Remember, 3 of them for the P6. 1, 2, 3. Then another one for the S, and then, oh, there's 3 here, but 2 would fill 1, so you may say 1. But in truth, there's no 2 coming together first. They'd be separated before they go together. So how many partially filled orbitals? You'd say 3. Okay, very important. And the magnetism we'll see in AP is due to that. All right. Okay. Argon is easy. Everybody's filled. It's a stable configuration. Moving on. Okay, I think we get the point here. Okay. So it's 3p6. It's a stable configuration, although it does not have a completely filled, 3s2, completely filled principal energy level. There's something about filling the S and P. So we get the idea. Sulfur -2, now that's very interesting. Sulfur, okay, if we look on the periodic table, it becomes charged. Okay, we're looking at 1s2, 2s2, 2p6, 3s2, okay, 3p1, 2, 3, 4, but because -2, it's the same as argon. Okay, and that's something you should have realized already. Okay, now, here are some questions that I was talking about before that we need to practice. How many filled principal energy levels are there? 1. How many occupied? That means having at least 1 principal energy levels. 2. There's at least 1 electron in this energy level. There's at least 1. Occupied, just having 1. How many filled sublevels are there? Filled sublevels. Well, S holds 2. This S holds 2. We know P's hold a maximum of 6. So there's only 2. This S and this S. How many occupied sublevels are there? Occupied means having at least 1 electron. This has at least 1. This has at least 1. And this has at least 1. So that would be 3. How many filled orbitals are there? Now, once you get into the orbitals, you better draw yourself a diagram if you don't see it. We have an S. We have another S. We know a P has 3 orbitals. And of course, here we go. And of course, 1, 2, 3, 4. So how many filled orbitals? 1, 2, 3. How many occupied orbitals? 1, 2, 3, 4, 5. At least 1 electron. So it's easy to get these wrong if you don't understand Hudd's rule and draw. Okay? Not tough questions, but they become particular. Okay, so what are we doing now? Now we're left with a couple different things left on the agenda, and that's excited states. Okay, now we've talked about excited states. Excited states are nothing more than states electrons exist in when they jump to higher energy orbitals. And I don't have a good drawing right here, so I'll draw one. So we talked about the Bohr atom. Here's a nucleus, and we're going to use shells, and we know that electrons exist in what? Waves. And we're defining these electrons in 3-dimensional shapes called wave functions, called orbitals. But we're going to use the rings just to make the same analogy. So electrons that exist closer to the nucleus have low energy. Electrons exist high energy. So we already learned that when you absorb energy, electrons, if they have enough, will get to this higher energy and become unstable. Now, because they're unstable, they will eventually leap back. When they do so, they give off the extra energy that got them to the higher energy level in the first place in the form of photons and light. And that's the red lines that we saw in the different color spectrums that we get. So what does it mean for an electron to leap to a higher energy level? That means it's leaving its ground state. If you notice, all our configurations we have been doing, we've been filling electrons from lower energy, not orbits, wave functions to higher ones. Always think the nucleus is in front, and the farther away the electron goes, the higher energy that that wave function or area or quotes orbit is. So anytime electrons leap away from the nucleus, energy is absorbed, and anytime they leap back, it's emitted. Okay, we've learned about that, but now we're going to apply that to here. Now, if we're looking for an excited state, it's the opposite of a ground state. Everything that we've done here is ground state. Electrons are going in order. What does that mean? It means I can't fill a P until I fill my S. Notice beryllium fills the 2 S's and not the P. It doesn't have a 5th electron. If it did, if this was boron, we would now be able to go into the higher energy. We have to fulfill the lower energies. Now why? Well, given the choice of low energy wave functions or orbits, electrons will go to low energy first before they go to high. That's just nature. Okay, things go to lower stable scenarios before they're forced to higher stable scenarios. Any case. So an excited state, my friends, in chemistry is a configuration where you would see electrons missing where they're supposed to be. For instance, oxygen is 1s2, 2s2, 2p4. But now, if it's excited, an electron jumped, okay, let's say from, I guess my drawing's terrible, from the 2s to the 2p5. So this actually should be here. Okay? And it leaves one less electron. So excited state configurations will have holes that I call holes, or places where electrons should be if they went in order. Well, they're not there because they gained electron and jumped away. Notice it was 1s2, 2s2, 2p4. Now it's 1s2, 2s1. There's one electron missing. It jumped to the 2p5. Okay, so here's some examples. Here's oxygen in the ground state. That's lowest level energy. Excited state means, whoa, one of these electrons leaped, or leapt, I should say, to the higher energy level. This is not going in order. You can't have a 3p electron before you fill the 2p, whereas our hole or a place where the electron should be right here. So an excited state configuration is configuration where we're showing electrons that have leapt or leaped away, all right? And they're leaving a spot where they should have been if they were in their ground state. Understand the electrons did not change in terms of number. So if I say oxygen in the ground state, oxygen atomic number 8. So we're still left with 1, 2, 3, 4, 5, 6, 7, 8 electrons in the ground state, and 1, 2, 3, 4, 5, 6, 7, 8 electrons in the excited state. I mention this because sometimes very famous questions have multiple excited states for questions, for like say multiple choice questions, and they'll say, which of the following is the excited state for oxygen? And some people would just pick the first excited state they see, but not count the electrons to see if it's actually particular for oxygen. Okay, it's an atom, so electrons equal to protons. So here's some examples. Identify the electron configuration that illustrates an excited atom. Okay, which one's showing me a hole? 1s2, 2s2, 2p6, 3s1. That goes in order. That's ground state. Okay, 1s2, 2s2, 2p1. Okay, also going in order. Okay, I can fill the 2p as long as the 1s2 and 2s2 are there. 1s2, 2s2, 3s1. Oh, this is a problem. We need to fill the 2p before we fill the 3s. So electrons are jumping away. This one should be, okay, if it was ground state, 1s2, 2s2, 2p1. So a 2p1 electron jumped to the 3s1. And this is the answer, okay, right here. Then the other one here is not excited. It goes in order. 1s2, 2s2, 2p6. It's going right in order. This is ground state. Okay, now of course we have Regents land configurations. If you haven't figured out, these are AP or the rest of the world use these, and New York State loves to give these very simple configurations. So the Regents will just have these. So I'm sorry if you feel like you had to learn so much more. But in any case, who's excited? Okay, well 2-8-1, I can only have one if I already have 8 filling the second. Well, that's ground state. Okay. Okay, 2-3. Well, my friends in chemistry, I cannot, well, I can. Well, if I'm going to fill 3 here, 2 has to be filled, so this is also ground state. 2-2-1. Well, there's your winner. You can't put 1 in the third until you fill 8 in the second. So this is the excited state. So this is your winner again. If you notice, it's exactly what this one is. This 1s2, 2s2, 3s1 is the same thing as 2-2-1. 2 in the first, 2 in the second, 1 in the end. This, of course, is the same as above here as well. So, okay, so pretty simple stuff. Okay, understand that when I talk about emission or absorption, okay, you're absorbing, you're going away from the nucleus. Here's the nucleus. Absorbing, emitting means you're going backwards. So a 3s is jumping back to a 2s. Remember, in configurations, the nucleus is in front. Careful with this because of overlapping. You should know that a 3d is farther away than a 4s. So a jump from a 3d to a 4s is emission. So be very careful about if you're going away from the nucleus or toward in terms of that. Valence electrons are electrons available for bonding. Okay, we've talked about that. They're rest electrons that are stable, or the kernel electrons. Okay, and I talked to you about looking for those. Okay, how many valence electrons here? Well, this is filled, this is filled, this is 6. Okay, and of course we did this in class, and for manganese, okay, we can say a couple different things. We can use 7 or pick one of its charges like we talked about. All right, and remember, very important for manganese, it has valence electrons from 2 different energy levels, from the D and from the 4s, the 4s electrons and the 3d electrons. All right, we talked about that in class. All right, I guess there it is. All right, there's the stable argon scenario, and here are the 2 valence electrons from 2 different energy levels. But the real deal, yes, it can become +7, but it also can be all of these as well. So these are all examples in real chemistry. Okay, the Regents would pick 7 there. All right, and that's the arrangement. And basically we're done here. Now for the last thing that we're going to do is electron dot diagrams, and very simple. The dots are valence. So for carbon, carbon is 1s2, 2s2, 2p2. This is filled, so there's 4 valence electrons. I do 4 dots. Where you put them, not really important. Okay, let's answer these questions. When an electron jumps from the 3d to the 4s, of course, energy is being released because you're getting back to the nucleus. And of course, how many valence electrons are found in this atom? 3d6, 4s2. Well, in truth, that's iron. Okay, you can say 8, I would accept, but you can do 3 or 2. When you look up iron, it tells you the 2 charges it likes to become. Okay, now dot diagrams, very simple. Okay, they're just the valence electrons. The only little catch up here, the only little hookup, or I should say difficulty here, is the noble gases. Argon doesn't have any valence electrons, but they like to show 8 for the noble gases to show that they're completely filled. It's called the octet. Helium is 1s2. They show 2 dots to show that it's filled. Okay, everybody else follows suit. And of course, you learned last year, sodium has 1 valence electron. Chlorine, as I have here, has 7. And the reason why this happens, chlorine needs 1 more to be stable, so it gains 1. And now it has that 8, or that noble gas configuration, and -1. Sodium lost 1, so now it's +1. And they stick together by opposite charges, and that's how sodium chloride, a lot of salts are made. 1Na+. Okay, hope that helps. See you tomorrow.